Hey everyone, and welcome to This Explainer. Today, we're unpacking a highly technical MATLAB Simulink model for a large battery energy storage system, or BESS. Drawing from a really comprehensive engineering framework by Wired White, we're going to dive into the practical reality of designing these systems. Look, if you're in the electrical industry, you already know that integrating renewables isn't just about plugging in some solar panels, right? It takes meticulous simulation. So, we're going to walk through exactly how to set that up to achieve absolute grid stability.
We've got a tight roadmap today. We'll start with grid stability and peak demand, move right into our step-by-step simulation setup, cover PV integration and system control, dig into frequency stabilization algorithms, and finish up with the economic benefits of storage. Let's get into it.
Section 1, Grid Stability and Peak Demand, or what I like to call the high-stakes reality of the power grid. Let's ground this simulation in the real world, specifically looking at a case study from Colombo, Sri Lanka. For industry pros, you know firsthand that managing the delicate balance between baseline supply and intermittent renewable demand is a massive, everyday engineering challenge.
So think of it this way. A BESS isn't just some giant passive battery sitting in a corner waiting for a blackout. It's a highly dynamic participant in the grid, actively doing the heavy lifting of peak shaving. During low demand, it quietly charges up, but when demand suddenly spikes and puts immense stress on the infrastructure, the system discharges power right back into the grid. Flattening that demand curve is absolutely crucial if we want to prevent localized brownouts or, worse, cascading grid failures. And we are operating under a razor-thin margin here. Maintaining grid frequency within precise 50 or 60 Hz limits is totally non-negotiable. Think about it. Even a 1% drop in frequency can literally tear apart the blades of traditional spinning turbines on the grid. It's that serious. The entire Simulink model we're examining today is specifically designed to keep the system locked onto this frequency completely regardless of the external load. To lock in that rock-solid stability, our simulation absolutely has to validate against core IEEE standards. No cutting corners. IEEE 1547 dictates exactly how distributed energy resources talk to the power system interfaces. And IEEE 2030.2.1 provides the literal blueprint for designing and operating the BESS. Ensuring we comply with these means the jump from a digital MATLAB model to a physical, real-world deployment will be seamless and, most importantly, safe.
All right, moving on to Section 2, Step-by-Step Simulation Setup. Let's look at executing the MATLAB Simulink environment.
Listen, if you're replicating this simulation yourself, you must follow this exact sequence. You can't just smash the Run button. Step 1, you've got to initialize your main input file. That loads all your structural parameters like the parallel connected strings for your solar arrays and your baseline grid requirements. Then step 2, and actually this is make or break, you have to run the weather forecasting script. This compiles a full year of environmental data, specifically average and minimum temperatures. Why? Because battery efficiency and solar irradiance are hugely temperature dependent. You need that real-world data in the workspace before you even think about step 3, which is finally executing the main MATLAB model.
Once that successfully runs, the software spits out these highly specific load dynamics. This is where you see the real-time system behavior. You can track load active power, which is the actual work being done, right alongside load reactive power, which, as we know, is vital for maintaining voltage levels. By analyzing these precise voltage and current profiles, engineers can spot the exact impact of time delays and perfectly optimize the converters and filters inside the model. Okay, Section 3, PV integration and system control. Let's see how harmonizing these subsystems actually works.
This is a beautiful dual control setup. On one side, you have the Battery Management System, or BMS. That's your strict safety watchdog. It's constantly monitoring the state of charge, and if things get abnormal, it automatically steps in and disconnects modules to prevent dangerous overcharging. On the flip side, the Maximum Power Point Tracking, the MPPT controller, is aggressively maximizing efficiency. It's constantly hunting for that optimal voltage from the solar panels, completely adapting to sudden cloud cover or temperature shifts. And tying the whole shebang together is the BES controller, which gets its marching orders from the Operator Control Room subsystem. Think of this as the brain of the operation. It lets operators dynamically adjust modes between peak shaving and charging based on real-time conditions, masterfully orchestrating the flow of power between the grid, the solar array, and the battery. Next up, Section 4, Frequency Stabilization Algorithms. We're getting into advanced grid control optimization here.
This is where we go from a reactive setup to a highly proactive one.
By injecting these specific algorithms into the BESS controller, we get predictive frequency regulation. This means using historical data to anticipate frequency changes based on forecasted loads rather than just panicking and reacting after a drop happens. We also use advanced energy management systems to switch modes on the fly, and the BESS actively coordinates with traditional synchronous generators and fax devices to optimize the whole grid's response to any disturbance. It's a real game changer.
But the holy grail of these algorithms is what we call grid-forming capability. This is massive. It means the system doesn't just follow the grid. It can operate completely autonomously. If the external grid completely blacks out, no problem. The BESS instantly switches into an islanded microgrid mode, acting as its own primary power source to provide that rock-solid voltage and frequency support, keeping local infrastructure up and running. Finally, Section 5, Economic Benefits of Storage. Let's talk about the financial payoff of all this grid stability.
Integrating a system like this fundamentally rewrites the economic model of energy storage. Because your BESS can react in actual milliseconds to stabilize the grid operators will literally pay you for that rapid regulation service. It completely flips the script, transforming your storage system from a simple, sunk-cost backup into a highly active, revenue-generating asset in modern frequency response markets. So, as we wrap up this explainer, we've covered the strict procedural setup, the dance between battery management and solar optimization, and the advanced algorithms that make grid forming a reality. The tools to build a more resilient and profitable grid are right here in the math. The real question is, as the energy landscape gets more volatile, are you just going to react to the chaos, or will you use these advanced models to dictate the stability of the grid yourself?